So today I'll be teaching on the slope deflection method, a method which is based on displacement method of analysis. And basically we are using this for statically indeterminate mostly, right? So uh, this method and the moment distribution method kind of gives you this same support bending moments, right? Support bending moments, but in the intermediate steps, you can have the displacement as well from the slope deflection method, right? So it considers the compatibility, the original shape of the structure, and then the equation, slope deflection equation is formed based on the uh, based on that shape, right? And we can go with this equation, right? So this is the slope deflection equation, you can see, right? So here, what they basically doing is, right? So you have uh, A and B. Let's say it's a continuous beam, and A and B is a general span. Okay, so you have loading, but in a real structure, your beam will bend like this, right? Right. So suppose if you support, you can have support settlement as well. So, okay. So you support something somewhere here as well, right? So in such case, you can use the slope deflection method. So this theta A and theta B. So what I was telling from the compatibility means, so this was the compatibility, that in the shape in the original, what? The original structure, right? So this is theta A, means the angle of rotation at A, right? So if the beam is continuous, this theta is same as this theta, right? So you can have, and you can have support settlements as well, delta, in any of the support settlement. So this support settlement is actually the delta called delta relative. I'll call you. I'll tell you what is delta relative, right? So theta B is the angle of rotation at B, right? So basically, if you don't know these things, right? You don't know these things, but you can find. So this equation have something to deal with the compatibility of the structure, but the original equation is formed what? On what? It's a force, right? So that means the equilibrium conditions, right? So it matches the equilibrium of this joint, right? That's how you get this slope deflection equation. This is at A. So AB basically means moment at A for AB member. So this is always, this first letter comes dominant, right? Moment at B for BA beam, right? So that means here. Moment at A for AB beam, that's here, right? So the fixed end moment is what happens if the what happened to the bending moment if the ends are fixed, right? So this is how you derive this slope deflection equation, basically through this uh, superposition, principle of superposition. So in this method, clockwise you always take, right? Always take clockwise as positive, right? Because this is derived in clockwise direction, right? So you can, so then the whole thing depends on your uh, sign convention, and if your clockwise is positive, so if theta is positive or negative. So if you apply it for a particular span, right? If you have several span in a continuous beam, so you apply for each span, right? for each span, you will have two equations, right? So theta A, if it is clockwise, that's positive. If it is anti-clockwise, it's negative. So if you have settlement, here's a trick how you take the settlement. So here originally you have a negative sign in front of the settlement term, but we take the clockwise settlements as well. Here's how you take. Let's say the beam is like this. So let's say this is A and B, and it seems your B is actually displaced, but that with respect to A, right? Let's say this is the original position. So if you need to consider it at A, right? So A, you need to consider whether it is clockwise or anti-clockwise. So you are taking it at A, right? This settlement of A. So that means you have to look it at with respect to B. So with respect to B, A has moved upward. That's all relative, right? B doesn't feel that he is displaced. It sees A has gone up, right? It sees A has gone up, but in which direction it has gone up? In anti-clockwise direction. The same thing when you apply it at B, right? When you apply it at B, the displacement B, right? You can see. Sorry, this is clockwise, right? This is clockwise displacement. Okay, so this is clockwise displacement, so that means this is positive, right? And when you apply it at B, you have to consider with respect to A, right? Why is that? We need the settlement is clockwise or anti-clockwise, right? So our clockwise is always positive, and compare with respect to A, right? This is the line of A. B has gone down delta, but in again in clockwise direction, right? So here's how you take the sign. That's very easy, right? So again, that is positive, right? Let's say, sorry, let's say you have some beam like this, right? And some beam, and then your, right? So when you apply slope deflection to these two parts, right? There's a delta support settlement, right? It's delta. When you apply to this portion, so you will have, let's say this is A, B, and C. So MAB, right? So you have some term, right? And you will have minus 3. This is delta or something. So you need to determine the sign of delta, right? Determine the sign of delta. How you take the sign is, so you take it at A. So you have to see it with respect to B. With respect to B, A has gone in clockwise direction, so your direction is positive. Similar to that, you will obtain when you apply it from B for this span, okay? For this span only, right? Compared to A, when you apply it at B, compared to A, it has gone in clockwise direction. That's positive, right? So let's say C, right? MBC, right? So minus 3 into. So now with respect to, so you are applying at B for this span, right? Span, and compared to C, now you have to look at B, right? Compared to C, your B has moved in anti-clockwise direction, so it is a negative delta, right? And when you look at it from C as well, right, you will see the same thing happens. Compared to B, C has gone up, right? B doesn't see that he is displaced, but it will relatively see the C has gone in upward direction, but in anti-clockwise direction, again minus delta, right? So this is how you take the sign of the sign of this delta, right? So we'll do an example. So we'll erase this, right? So we'll apply this for the time being. I will do this example, right? So first thing is you have how many spans? AB and BC. You have two spans, right? Okay, you have two spans. You have to apply slope deflection equation for each span, right? So for each span, you will have to apply it two times. You have to apply it at A and you have to apply it at B. You have to apply it at B again and you have to apply it at C. From these four equation, right? These four equation, you can find theta A, theta B, and theta C. And if there's any delta, right? So delta should be given, but if not, yeah, delta should be initially given, otherwise it will be another unknown, right? So yes, we can now find like this. So MAB, so I'll apply for this one. Right. MAB. First thing is the fixed end moment. So for this one, the fixed end moment is WL squared over 2L, right? WL squared over 2L, right? This one. W is 40. L squared over 2L means W. That's going to be 120. That is anti-clockwise, right? So you can take it from the appendix, any appendix in the Google, fix and just type fix and moments, right? So this is minus 120, right? So beam is perfectly in same EI, right? Otherwise, you will have to substitute for that. This is 2EI over L. So I think there's some 2EI over L. L is 6, right? So now your unknowns. Here you have theta A, right? Right. Theta A have some known value. I'll discuss it later, right? Because this is a fixed support. Theta A is 0, right? Your beam will bend like this, right? You will have theta C here. You will have both theta B here. Right? So you have 2 theta A plus theta B, and you don't have any support settlement, so that it is 0. If you have it, you have to, so they will give the value so that you can find these unknown rotations, right? Okay, so Then for MBA, so that is friction moment at BA, so that is plus 2, that is minus WL squared over 2L and plus WL squared over 2L, right? Plus WL squared over 2L, then 2EI over L, and so when you apply, then it's B, right? So always you have the same letter front, right? So this is the leading, theta B, theta B, theta A, then this is the rotation at the other end, right? To theta B plus 2 theta A minus, so you don't have any support settlement, right? So we have now applied for BA span, right? So the entire AB span is now done. I have applied for AB at A and AB at B, right? So I have to apply for BC span at B and C. So I will apply B and C, right? So that's going to be MCB, sorry, MBC, right? Right, BC. So you have point load, and the fixed end moment is, because fixed end moment, right? Fixed end moment is going to be PL over 8, right? L is 2, so that's going to be 120 over 8, right? So your fixed end moment is going to be 60 into 2 divided by 8, so that's going to be 15. So here again at the left end you have anti-clockwise movement. These only for the fixed moments, right? You can take it from any appendix. Appendix give you the direction and the magnitude, right? So here you have minus 15, right? Plus 2EI, same EI in that part as well. If they gave it like this is EI and this is 2EI, right? Here no need to change it. Here you have to substitute 2EI, right? This is L is 2, right? Okay, so 2 theta B plus theta C. No support settlements in that span, any of the members, right? So, and MCB, that's going to be plus 50, that's fixed end moment is clockwise. Right, and this is going to be 2EI over then 2 theta C theta B C, right? Now you know that if you, yes, you already have this one, right? So these are the 4 equations, right? So you have 4 equations, and see what's the problem now, right? You have to find, first you have to find theta, right? Otherwise you can't find MAB, right? So to find theta, you need to get rid of these ones, right? Because these things also you don't know, right? So how do you find this one? So you consider the equilibrium of a joint, right? So that, you know, you can form an additional equation. And another thing, your theta A is 0 because it's a fixed support, right? Either your pin or roller that will have theta, but this is actually 0, right? And this bending moment MAB is not 0, right? Because that's a fixed support that you will have uh, unbalanced bending moment. So bending moment, right? So that will have a reaction and you have a bending moment. And here the bending moment is balanced and the total, right? So MBA plus MBC, right? You know the total bending moment summation at this joint pin or roller, right? Internal pin or internal roller, or at the end rollers or end pin, right? You know the summation of bending moments about that point is 0, right? So that means you have MBC and MBA plus MBC should be 0, and that way you can get rid of MBA and MBC and form another equation, right? So this will give you something, and you know this equation is also MCB is also total bending moment is 0, right? You have only one member and that is 0, and you will get an equation from theta B and theta C only, right? Right, equals to something. Here also you will get theta C, theta B, and theta C equals to something. From that you can find theta. So you have two equation and two unknowns, right? And you can find theta B and theta C, right? So we'll go ahead and find. So if you add these two, that gives you 0. So this gives you 105. So you adding these two together, right? But you can't add this one because 2 EI over 6 and 2 EI over 2, right? So you have to basically, what you can do is you can multiply this by 3 and you can multiply the same as 3. So this is 6 EI over 6. This is 2 EI over 6, but you can add now, right? So this is going to be 4 EI theta B over 6, right? So that's going to be actually a 2 EI theta B over 3, right? And from the second equation, you will have 2 is getting cancelled. 6 sorry, 2 is getting cancelled. 6 EI theta B over 3, right? Six EI theta B over 3, right? And then you have this one. 2 is getting cancelled. 3 EI theta C over 3. So why I didn't cancel these 3 is I can simplify still, right? So this will give you 105 plus 8 EI theta B over 3 plus, if you want, you can just simplify or not, right? Right. EI theta c over 3. Right? So this is our first equation, right? And it's equal to 0. Okay. So from the second equation, you will get, this is directly 0 because the entire bending moment you will have only one members. You have here two members. That's why I add these two and equate this to 0. If you had like three members, you have to add three. You will have to add three equation and make it 0. Okay. So this is 15. This is 2EI. That's going to be 4EI. So 2 is getting cancelled. 2EI theta C plus EI theta B. Plus theta B, right? So I can take this into, I can take this 15 into the other side. Okay, so that's going to be negative 15. And I can take this 105 into other side as well. So, so I can multiply this by 3, right? So there's going to be 350. That's going to give you EIOIE and so 3I theta C. Right. So the easiest way to solve is you can multiply the first equation by 8. Right. 15 into 8 is that's going to be, so you multiply it by negative 8. Okay. It's going to be negative 16 EI theta C minus 8 . So you will add these two together so that 8 EI will cancel and you will get minus 13 theta C is 120. So theta C is what? Theta C is 120 over 15. So 9.23 over EI. And that is negative. So negative sign means this theta is anti-clockwise, right? Theta is in anti-clockwise direction, and you can calculate easily theta B from this equation, right? Because you know theta C, right? So that's going to give you 15. So I'll take this as into this side, minus 2 EI. Theta C is 112 over 13 EI. So that negative is going to be cancelled with this negative and make it positive, right? Doesn't matter. I will write that. Otherwise, confusing for the people who see this. Right. So here, so EI is the denominator. So that's going to give you what? How much? Minus 15 plus 240 over 13. 45 over 13. So that's give you 3.46. So that's positive over EI. That's theta B, right? Positive. So that means that is in the clockwise direction, right? So that is how you get this sign, right? So once you take the bending moments, right? Theta B and theta C, now it's done. So you can plug them back. So theta A is 0, you know that. Theta B you found, theta C you found. Everything is known. And then you can plug into each equation, find MAB, find MBA, find MBC, find MBC. So once you find MBA, you know addition of these two will give you 0. So that MBA is negative MBC, right? This is anyway 0. You don't need to plug anything to that, right? Because that's just one member and roller support. So you know the bending moment should be 0. So when you plug it, so you can plug them back into this equation and find the MAB, MBA, MBA, BC, and MCB value. This is anyway 0, right? You know the reason though. So the summation of these two is 0. If you find this one, right, so that is equal to, so you don't need to again plug it back to MBC equation because MBA is negative MBC. That's how the addition becomes 0, right? You take it to the other side. We always worry, so you don't need to worry on the side. The answer will give you the sign, right? If you have followed the sign convention well, properly, that will give you negative if it's anti-clockwise, and so that and this will also have some value, right? So that the idea is, overall idea is, if you have some indeterminate beams, right? So now you know from the slope deflection method, you even know the displacement as well, rotations, and you know the bending moments as well. So this is no longer remains a complex problem. So this is anyway 0, right? Okay. So that if you know the bending moment, you can separate it. Let's say you have a shear force. So here you will have two components, right? One is from this member, the other one is from this member, right? So when you separate it, you have to separately take it out, right? You can separate the beams, right? So now these are in equilibrium with these forces, right? So you don't worry on the sign of the bending moment. You will be given from the final output of the slope deflection method, right? So you can take each beam, each span, and separately solve for these reactions. Since you know the bending moment, let's say you had some loading on this beam, so you can take the sigma vertical in horizontal vertical direction, and you have R1 and R2, and you take bending moments about 1 point for this span, right? So you have this. If you take around this moment will come, this reaction will not come, this loading will come because it at the middle of the beam, right? And this moment will come, and this R2 bending moment will come, so you can find R2. Similarly, from the vertical equilibrium, you can find R1. Likewise, you can find for each one. So when you find R3 and R2, right? So that will give you the total reaction at B is R2 plus R3, right? This is anyway R1, this is R4. From that, you can find the shear force diagram, right? And from this location, you can draw the bending moment diagram since you know the loading as well, right? So hope you understand the summary of the slope deflection method, right? Thank you.